Alright, we're now going to start looking at some absolute value inequalities, and you might remember from when we were looking at absolute value equations that there was a graphical or geometric interpretation of an expression that looks like this. And what we were saying is that it meant that the distance, because absolute value represents a distance or a magnitude, the distance between our unknown value x and the point on the number line 2, the distance is equal to 3 units. And remember then that our central point was at 2, and we knew that we could go 3 units to the right side or 3 units to the left side of 2, and that would give us our two values. And that kind of gives us an idea about how we can interpret absolute value inequalities. So let's use a graph to try to solve something like this. We can interpret an expression like this to mean that our distance from positive 3, so let's make a positive 3, our distance from positive 3 must be greater than 2 units. So let's go 2 units to this direction, and I'm going to do a open circle 2 units to the right. Okay, this is my distance of 2 units. And I've got my 2 units to the left side, which brings me to 1. So 2 units each way, and I'm going to make these open circles because I know that my distance must be greater than 2 units away. If I shaded in 5 and 1, that would be equal to 2 units away, but it must be greater than 2 units away. So it's all points more than 2 units from positive 3. And here's a graph from my expression. And now I can clearly see then that my solutions are x is less than 1 or x is greater than 5. I'm not going to continue doing formal set builder notation and interval notation for all of these problems, but I will do it for this one just to remind you. Formal set builder notation, x, all values x, such that x is an element of the real numbers, and we have additional restrictions, x is less than 1 or x is greater than 5. Or in interval notation, we've got everything from negative infinity up until 1, not included. Union, because we're adding on an additional region, that goes everything from positive 5 up to positive infinity. Alright, example n. Let's use a graph to solve this situation. So now, instead of having a positive 3, instead of measuring the distance from positive 3, we're now measuring the distance from, can you imagine if we rewrote this? X minus negative 1. We're measuring the distance from negative 1. So I suppose you can remember then that the distance that we're measuring from, that central point, is always the opposite of what we see here. In this case, a negative 1. The distance from negative 1 must be less than or equal to 3 units. So if I go 3 units to the right, that brings me up to 2. And if I go 3 units to the left, that's going to bring me down to negative 4. And I know that I am allowed to possibly be equal to 3 units away. So let's shade those in. Or my distance can be less than 3 units away. Well, these points are all less than 3 units away. In fact, I end up shading everything, including the negative 1 itself, because that would be a situation where my distance away from negative 1 is equal to 0 units, and that, of course, is less than or equal to 3. If I was expressing this, okay, so sorry, I can clearly see that my value is negative 4 is less than or equal to x is less than or equal to 2. And I'm not going to bother with set builder notation or interval notation anymore. I think you've got the idea. Well then, it should be possible to write an absolute value equation or an absolute value inequality that describes a solution set that is being given to you already as a graph on a number line. So suppose that we've been given this situation, we need to write an absolute value equation that describes that solution set. Well, I've got 2 solutions only. That's going to be an absolute value equation. My middle point in between negative 4 and positive 6, if I take the average of these 2 values, I'll see that my middle point is at positive 1. And so my distance of my 2 solutions, my distance between my solutions x and positive 1, is exactly equal to, what's that distance? 5 units each way, 5 units. And now I've written an absolute value equation whose solution is described by this graph. Example P. We need to write an absolute value inequality that describes this graph. Again, let's start by finding the middle point. The average of negative 19 and negative 3, we can find the average easily by adding them together and dividing by 2. Negative 22 divided by 2 is negative 11. That's the middle point. It's pretty quick for me to see that I'm 8 units away each side. So my distance between x and negative 11, so again I'm putting the opposite sign, my distance must be less than 8 units. If I went a full 8 units away, I would no longer be a part of my solution set. So my distance must be less than 8 units away. For example, my solution set includes all of these points, all of whose distance is less than 8 units away from that central point of negative 11. Lastly, example Q, let's write an absolute value inequality that describes this graph. We'll start by finding the middle point. 2 plus 15 is 17 divided by 2, that's 8.5. So my distance between x and that middle point, 8.5, this time my distance is greater than or equal to, what is that distance? That looks like a distance of 6.5. So my distance away is greater than or equal to 6.5 units from my central value. Alright, so I'm not going to read you this entire paragraph, but I will try to highlight a couple of important areas. A good strategy to solving inequalities with absolute values in an algebraic manner is to isolate the absolute value and then split into two cases. But there's two different ways of doing this kind of problem, and I want to show you both ways as we go. You know that how we were solving the absolute value equations, we just turned the right-hand side, you know, the part on the right that did not have the absolute value, we just turned the right-hand side into a positive case and a negative case. And you can certainly do that with absolute value inequalities as well, but in the negative case, you would have to switch the direction of the inequality. Now that can be a bit confusing for students. I will do that the first time, but then I'm going to show you another way that you can handle it so you can avoid that issue. Let's do example Q. Oh, whoops, I need to fill in a couple of blanks, don't I? It's important, nevertheless, to isolate the absolute value expression so we can decide whether the positive and the negative cases that we get, whether they form an AND situation or an OR situation. We're going to get an AND inequality if the isolated absolute value expression is less than the other side of the inequality. And we will get an OR situation if the isolated absolute value expression is greater than. So just to summarize this, less than, we've got the absolute value expression is less than or equal to, and the OR situation is where we've got the absolute value greater than or equal to. So that's an AND, and that's an OR. Okay, here we go. Example Q. Let's start by isolating the absolute value much as we've done before. So we'll bring the 1 to the right side. It becomes 7 minus 1 is 6. Let's divide both sides of the equation by positive 3. That means I don't have to change the direction of the inequality. There we go, divided both sides by 3. Now look, I've isolated my absolute value expression, and it is greater than. So is it AND or OR? It's an OR situation. So when we split into two cases, we'll separate them with an OR. So first of all, let's just take away the absolute value sign. There's my first case. And in my second case, if I'm going to change my right-hand side to a negative 2, I must switch the direction of the inequality in that second case. Alright, now we can finish. If I bring the 2 over, subtract 2 from both sides, negative x is less than 0, divide both sides by negative 1, and x will be less than 0. Or, subtract 2 from both sides here. Negative x is less than negative 4. Divide both sides by negative 1. X is greater than positive 4. So there's your solution. X is less than 0 or x is greater than 4. Example R. Again, let's isolate the absolute value before we do anything else. So I'll bring my negative 1 to the right-hand side, and it becomes a positive 1, giving me 2x minus 4. Now let's divide both sides of the equation by negative 2 to isolate the absolute value. And if we're dividing by a negative number, the inequality switches directions. If we divide 2x by negative 2, it becomes negative x. If we divide negative 4 by negative 2, it becomes positive 2. Now we're ready to switch into the to split into two cases, I should say. Our first case, we simply take away the absolute value, and nothing else changes. Is this an AND situation or an OR situation? Well, we have the absolute value is less than. That makes it an AND situation. So let's split into the two cases. X plus 4 is, let's do this again. I've already written my first case. My second case then, and x plus 4, let's switch the sign of the inequality, and we'll take the negative of the right-hand side. That's the negative of the negative x, positive x, and the negative of the positive 2, negative 2. Alright, let's continue. I'll bring the x's to the left. This negative x becomes a positive x, giving me a total of 2x. And on the right, this positive 4 becomes a negative 4, giving me a total of negative 2. And in this side, we'll subtract the x from the left-hand side as it moves across, and that gives me 0x. And the positive 4 on the other side will become a negative 4, yielding a total of negative 6. This means then that x is going to be less than or equal to negative 1. And now 0x is the same thing as 0, isn't it? Is it true that 0 is greater than or negative 6? Remember how to handle a situation where your x's have cancelled out? This is always true for any value of x. So this particular situation here can be interpreted as all reals. So let's look at our final answer. X is less than or equal to negative 1 and all reals. It's very helpful to graph this on a number line so we can see what's going on. X is less than or equal to negative 1. I'm going to graph this above the number line to look for the region of overlap because it's an AND situation. So x is less than or equal to negative 1. And something that's always true. All reals is my second condition, the entire number line. What's the region of overlap? I can see that the region of overlap is everything from negative 1 and downwards. And so my final solution, thanks to my number line helping me out with the region of overlap, is x is less than or equal to negative 1. Now, if you've got two absolute value expressions, you'll first have to isolate one of them and split into two cases. And then in each of those cases, you'll have to isolate the other absolute value expression and split into two further subcases. Now, I could do this. I'll just start it out. One of my absolute values has been isolated already, so when I take away that absolute value, my first case is going to be like that. And my other case, this is an AND situation, isn't it? Because my isolated absolute value was less than. And x plus 4 is greater than the opposite, the negative of my right-hand side. Okay, now it might be helpful to put my absolute value on the left, so I'm just going to rewrite this. 2x minus 2 is greater than x plus 4. And I'll move this absolute value equation, well, let's just divide, I'll just move it to the left, it's easier, it becomes a positive 2x minus 2 in absolute value. And I'll move the x plus 4 over to the right-hand side, becomes a negative x minus 4. And now I'm ready to split again into two situations. I'm not going to continue, but we could split here into two situations that will be separated by an OR. And here we'll split into two situations that will be separated by an OR. And then we'll end up with a solution here and region of overlap, a solution here.